Right now, at this very moment, you might glance up at the night sky and see our moon hanging there, so familiar, so constant, that it's easy to imagine it has always been exactly where it is. But the moon in our sky tonight is the result of one of the most violent, beautiful, and transformative events in the entire history of our solar system. A cosmic collision so profound that it didn't just give Earth its companion, it fundamentally changed what our planet could become. Welcome to Sleep About Science. Tonight, wherever you are in the world, we're exploring the moment Earth got its moon to its story that begins 4.5 billion years ago with destruction and ends with the very forces that may have made life on Earth possible. And if you drift off to sleep while listening, that's perfectly wonderful. Before we begin, please make yourself comfortable. So to right, the same of your clothes, pull your blankets up to just the right level and let yourself settle into that perfect position for rest. Remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to so you never miss these gentle journeys into science. And if you find value in these explorations, a gentle tap of the like button helps more people discover the wonder of sleepy science. Now, imagine traveling back in time, not just years or centuries, but billions of years, to when our solar system was young and chaotic. The Earth you'd find there would be utterly unrecognizable, a hellish world of molten rock and toxic atmosphere, bombarded constantly by asteroids and comets. This wasn't the blue marble we know today. This was a planet still finding its form, still being shaped by the fundamental forces of gravity and collision that were sculpting all the worlds around our young sun. Picture our solar system at this time as a cosmic construction zone. Rocky debris left over from the sun's formation was still scattered throughout the inner solar system like cosmic gravel. These chunks of rock and metal, some as small as pebbles, others as large as small planets, were following chaotic orbits, constantly colliding and merging and breaking apart again. It was during this violent period, called the Late Heavy Bombardment, that something remarkable was about to happen. Bells, something that would give Earth the most prominent feature in our night sky. To truly understand this story, we need to step back even further to the very beginning of our solar system's formation. About 4.6 billion years ago, in a quiet corner of our galaxy, there was a vast cloud of gas and dust called a nebula. This cloud, perhaps 10 times the mass of our current solar system, was slowly rotating in the darkness of space, held together by its own gravity but stable and unchanging for millions of years. The nebula that would become our solar system was not unique in the galaxy. Throughout the Milky Way, similar clouds of gas and dust drift through the darkness, most of them destined to remain unchanged for billions of years. These molecular clouds, as astronomers call them, are the stellar nurseries of the galaxy, vast cold regions where stars are born when conditions are just right. Our particular nebula was composed primarily of hydrogen and helium, the most abundant elements in the universe, but it also contained heavier elements carbon, oxygen, silicon, iron mines that had been forged in the nuclear furnaces of previous generations of stars and scattered into space when those stars died. These heavier elements made up only a small fraction of the nebula's mass, but they would prove crucial for the formation of rocky planets like Earth. For perhaps millions of years, this cloud drifted through space, slowly rotating, occasionally gaining or losing small amounts of material as it encountered other gas clouds or the stellar winds from nearby stars. It was a stable system, held in delicate balance between its own gravity, trying to collapse it, and the internal pressure of its gas, trying to expand it. Then something disturbed this cosmic tranquility. Perhaps it was the shock wave from a nearby exploding star, a supernova, whose death throes sent ripples through space at tremendous speeds. Or maybe it was the gravitational influence of a passing stellar system whose gravity squeezed and distorted our quiet nebula. Whatever the cause, this disturbance triggered the collapse of the nebula, and what followed was one of the most fundamental processes in the universe, the birth of a star and its planetary system. As the nebula began to collapse under its own gravity, it started to spin faster, like a figure skater pulling in their arms. This is due to the conservation of angular momentum, a fundamental principle of physics that governs rotating systems throughout the universe. As the cloud contracted, it had to spin faster to maintain its total angular momentum. The collapse wasn't uniform. The center of the cloud, where gravity was strongest, collapsed fastest, becoming increasingly dense and hot. As more and more material fell toward the center, the temperature and pressure there began to climb dramatically. Meanwhile, the rotation of the collapsing cloud caused it to flatten into a disk, with most of the mass concentrated in the central bulge that would become our sun. This process took perhaps a few 100,000 years, incredibly fast by cosmic standards, but still longer than all of recorded human history. As the central region continued to contract and heat up, something remarkable happened. When the temperature at the core reached about 10 million degrees Celsius, hydrogen nuclei began to fuse together to form helium, releasing tremendous amounts of energy in the process. Nuclear fusion had begun, and our sun was born. The moment the sun ignited was a turning point for our entire solar system. The sudden outpouring of energy from nuclear fusion created a powerful stellar wind, a stream of charged particles flowing outward from the sun at hundreds of kilometers per second. This solar wind began to blow away much of the remaining gas in the solar nebula, but not before some remarkable processes had begun in the flattened disk of material surrounding the new star. Within this protoplanetary disk, as astronomers call it, the temperature varied dramatically with distance from the sun. Close to the star, where the infant Earth would eventually form, temperatures were high enough that only the most heat-resistant materials could condense into solid form. These refractory materials, metals like iron and nickel, and rocky minerals like silicates, began to condense out of the gas like cosmic snow, forming tiny solid particles that would become the building blocks of the terrestrial planets. Farther from the sun, where temperatures were cooler, water ice could condense along with the rocky materials. This is why the asteroids in the outer regions of the asteroid belt contain significant amounts of water, while those in the inner regions are dry and rocky. Even farther out, beyond what astronomers call the snow line, even more exotic ices could form as frozen carbon dioxide, ammonia, and methane methanterials that would eventually become incorporated into the giant planets and their moons. The process of planet formation began with these tiny grains of dust and ice, each no larger than the particles in cigarette smoke. And first, they stuck together through electrostatic forces, the same static electricity that makes dust cling to your television screen. These microscopic particles gradually accumulated into larger aggregates, which in turn collided and merged to form even bigger objects. This early stage of planet formation is called accretion, and it's a surprisingly delicate process. The growing dust particles had to be just the right size, large enough to have significant gravitational attraction, but not so large that collisions would destroy them rather than merge them. The conditions in the solar nebula had to be just right, as well enough turbulence to bring particles together, but not so much that it would tear them apart. Over hundreds of thousands of years, this gradual accretion process created objects ranging in size from pebbles to boulders to small asteroids. These larger objects, called planetsimals, were the true building blocks of the planets. They were large enough to have significant gravitational attraction, which allowed them to sweep up smaller objects in their paths and grow even larger. The formation of planesimals marked the beginning of a more violent phase of planet formation. As these objects grew larger, their collisions became more energetic. When two planetimals crashed into each other, the impact might completely shatter both objects, sending fragments flying in all directions. But over time, the larger fragments would be recaptured by gravity and reassemble into even bigger objects. This process was inherently chaotic. Computer simulations of early planet formation show that many more planetary embryos formed initially than could survive in stable orbits. Some of these growing worlds collided and merged, while others were ejected from the solar system entirely by gravitational interactions with the forming giant planets. It was a cosmic game of musical chairs, with only the luckiest participants ending up in stable orbits. The inner solar system, where Earth was forming, was particularly violent during this period. The rocky planetimals that were moving at high speeds, driven by the gravitational influence of the forming planets and the chaotic dynamics of the early solar system. When these objects collided, they generated enormous amounts of heat, so much heat that the growing planets remained largely molten for millions of years. It was during this period of heavy bombardment and planetary growth that Earth began to take recognizable form. Our planet grew through the accumulation of countless planetesimals, each impact adding mass and energy to the growing world. The largest impacts would have been spectacular events, temporarily melting vast areas of Earth's surface and sending plumes of vaporized rock high into the atmosphere. But Earth wasn't the only world forming in this region of the solar system. Scientists believe that the early solar system contained many more planetary embryos than we see today. These worlds were competing for the same pool of raw materials, the planet semels and debris left over from the solar nebula's collapse. Most of these embryonic planets were destined to be destroyed in collisions or ejected from the solar system, but one of them would play a crucial role in Earth's story. This world has been given the name Theia, after the Greek Titaness, who was the mother of Selene, the moon goddess. Theia was roughly the size of Mars, about half Earth's diameter, and containing roughly 10% of Earth's current mass. Like Earth, Theia was forming through the gradual accumulation of rocky planesimals, slowly growing larger as it swept up debris in its orbital path. The early Theia would have been a fascinating world in its own right. Being smaller than Earth, it would have cooled more quickly, possibly developing a thin, solid crust while Earth's surface remained largely molten. But like all the terrestrial planets during this period, Theia was still experiencing frequent impacts from asteroids and planet simals, which would have kept parts of its surface molten and constantly reshaped its topography. The interior structure of early Theia was probably similar to that of the young Earth, though on a smaller scale. The process of planetary differentiation, where dense materials like iron sink to form a core, while lighter materials rise to form a mantle and crust, was probably well underway in both worlds. This process is driven by the heat generated from countless impacts and the decay of radioactive elements, and it's what gives terrestrial planets their layered structure. For tens of millions of years, Earth and Theia followed separate evolutionary paths in the young solar system. Both worlds continued to grow through the accretion of planesimals, and both were gradually cooling as the rate of major impacts began to decrease. The chaotic early solar system was slowly settling into a more stable configuration, with fewer large objects remaining to collide with the growing planets. But the gravitational dynamics of the early solar system were complex and unpredictable. The massive outer planets, Jupiter and Saturn, were exerting powerful gravitational influences on the smaller objects throughout the solar system. Their gravity could redirect asteroids and planesimals, sending some toward the inner solar system and others out toward the edges of the planetary realm. It was probably these complex gravitational interactions that eventually put Theia on a collision course with Earth. The exact details of how this happened are still debated by scientists, but computer simulations suggest several possible scenarios. Perhaps Theia formed at one of the Lagrange points in Earth's orbit, stable gravitational zones where objects can remain in equilibrium with both Earth and the Sun. As Theia grew larger, it might have become gravitationally unstable and begun to drift away from its Lagrange point, eventually entering an orbit that would intersect with Earth's. Alternatively, Theia might have formed in a completely different part of the solar system and been redirected toward Earth by gravitational interactions with other planets. The early solar system was much more dynamic than it is today, with planetary orbits that were still evolving and objects that could be redirected from one region to another. Whatever the mechanism, the result was the same. Theia found itself on a collision course with Earth. This wasn't a quick process. The gravitational interaction between the two worlds would have been building for thousands, perhaps millions of years before the actual collision occurred. During this time, both planets would have been experiencing increasingly powerful tidal forces as they influenced each other's shapes and internal structures. The approach of Theia toward Earth would have been a slow motion catastrophe of cosmic proportions. As the two worlds drew closer together, their mutual gravitational attraction would have begun to deform both bodies. The surfaces of both planets, still partially molten from the heat of formation, would have bulged toward each other like two drops of water approaching contact. These tidal deformations would have created tremendous stresses within both planets. The constant flexing of their crusts and mantles would have triggered massive volcanic eruptions and earthquakes. The surfaces of both worlds would have been in constant flux, with new mountain ranges of solidified lava forming and melting away in cycles measured in years, rather than the millions of years such processes take today. Imagine standing on the surface of either world during this final approach, though of course no life could have survived in such conditions. The Ea would have appeared as a growing disk in Earth's sky, no longer a point of light, but a world that filled an increasingly large portion of the heavens. The gravitational stress would have created winds unlike anything we can imagine, as the atmospheres of both worlds were drawn toward each other. The very shapes of both planets would have been changing as they approached. Instead of the spherical forms we associate with planets, both Earth and Theia would have become increasingly elongated, stretched toward each other by their mutual gravitational pull. The tidal forces would have been so strong that both worlds might have looked more like cosmic teardrops than spheres. The two worlds drew to within a few thousand kilometers of each other. The gravitational forces would have become overwhelming. The surfaces of both planets would have been rising and falling like giant slow waves, with tidal bulges hundreds or even thousands of meters high. Massive amounts of material would have been stripped away from both worlds and begun falling toward their mutual center of gravity. The final moments before impact would have been spectacular beyond imagination. Picture two molten worlds, their surfaces glowing red and orange in the darkness of space, approaching each other at a speed of several kilometers per second. The point where they would first touch would have been visible as a growing bright spot, where the intense tidal forces were already beginning to vaporize rock and metal. Scientists believe the collision occurred at a speed of approximately 11 kilometers per second, more than 30 times faster than the speed of sound on Earth. At this velocity, the kinetic energy involved was equivalent to roughly 100 million times the energy that would be released if all of Earth's nuclear weapons were detonated simultaneously. But this wasn't just any collision, the angle and speed were precisely right to create something unprecedented in our solar system's history. The impact was what scientists call a glancing blow. Theia didn't strike Earth head on, but rather hit at an oblique angle of about 45 degrees. This angle was crucial. A direct head on collision would likely have completely destroyed both worlds, creating nothing but a field of debris that would have eventually been scattered throughout the solar system. A collision at too shallow an angle might have caused Theia to bounce off Earth, leaving both worlds damaged but essentially intact. But the angle of this particular collision was perfect for creating something new and remarkable. Instead of complete destruction or a mere grazing impact, the collision initiated a complex series of events that would ultimately result in the formation of two new worlds, a larger, transformed Earth and our moon. The moment of impact was the most spectacular event in our planet's history. When the Fritia's surface first touched Earth's, both worlds began to merge and tear apart simultaneously. The tremendous kinetic energy of the collision was instantly converted into heat, creating temperatures that exceeded 10,000 degrees Celsius, hotter than the surface of the sun. At these temperatures, solid rock doesn't just melt, it vaporizes instantly, creating an expanding cloud of superheated gas and plasma. The point of impact became a growing fireball that quickly engulfed both worlds, turning solid matter into a glowing, expanding sphere of vaporized rock and metal. The primitive atmospheres of both planets were instantly stripped away, joining the growing cloud of superheated material. But the collision wasn't symmetrical. Because of the glancing angle of impact, different parts of both worlds experience different fates. The dense iron cores of both planets largely survived the initial impact, with Theia's core eventually merging with Earth's core. This merger was crucial for Earth's future development, as it helped establish the powerful magnetic field that protects our planet from harmful cosmic radiation. Meanwhile, the less dense rocky material from the mantles and crusts of both worlds was blasted into space by the tremendous force of the collision. This material, superheated rock vapor, and molten debris didn't escape Earth's gravity entirely, but instead began to form a massive, glowing cloud around the transformed planet. Let's pause for a moment to imagine what Earth looked like immediately after this cosmic catastrophe. The entire planet would have been glowing like a small star, its surface temperature perhaps exceeding 2000 degrees Celsius. The collision had added so much energy to the Earth system that the entire surface was molten nine, a global ocean of liquid rock radiating heat into space. The atmosphere would have been composed entirely of rock vapor, silicon, magnesium, iron, and other elements that we normally think of as solid, all existing as gases at these extreme temperatures. This rock vapor atmosphere would have been incredibly dense and hot, glowing with its own light, like the atmosphere of a star. Above this transformed Earth, one of the most remarkable structures in solar system history was taking shape. The material blasted into space by the collision, perhaps equivalent to several percent of Earth's total mass, was settling into a disk around our planet's equator. This wasn't the thin, elegant ring system we see around Saturn today. This was a dense, chaotic mass of material ranging from microscopic particles to mountain sized chunks of molten rock, all orbiting in a thick disk that extended from just above Earth's surface to perhaps twice the distance of the Moon's current orbit. The disk of debris would have been a sight to behold if there had been any observers present. Imagine looking up from Earth's glowing surface and seeing not the familiar black of space, punctuated by distant stars, but a brilliant arc of white hot material stretching across the entire sky. The individual chunks of debris would have been visible as they moved through their orbits, some glowing white hot from the heat of the collision, others already cooling to orange and red as they radiated their energy into space. The temperature within the disk varied dramatically with distance from Earth. Material close to the planet remained hot enough to be completely vaporized, neas a glowing gas of rock, vapor, and metal atoms. Farther out, where temperatures were somewhat lower, tiny droplets of molten rock began to condense from the vapor, like raindrops forming in a cloud. These droplets, still glowing with heat, began to collide and stick together, forming larger and larger aggregates. The physics of this process were extraordinarily complex. The disk was turbulent, with currents and eddies of hot material flowing in chaotic patterns. Electromagnetic forces played a role as well, as the hot ionized material created magnetic fields that influenced the motion of charged particles. But underlying all this complexity was the fundamental force that would ultimately shape the moon gravity. As the larger chunks of material in the disk grew bigger through countless collisions, their gravitational influence began to dominate their local regions. This marked the beginning of the moon's formation, a process that would transform the chaotic debris disk into a single large satellite within just a few hundred years. The moon's accretion from the debris disk was remarkably rapid by geological standards. Computer simulations suggest that perhaps 90% of the moon's mass accumulated within the first century after the collision, with the remaining material being swept up over the following few hundred years. This rapid formation explains many of the moon's unusual characteristics, including its relatively small iron core and its similarity to Earth's mantle composition. But the formation process was far from gentle. The growing moon was constantly bombarded by debris from the disk, with impacts occurring perhaps every few minutes during the most intense period of accretion. Each impact generated heat, keeping the moon's surface molten even as it grew larger. The largest impacts would have created explosions visible from Earth, temporarily disrupting the formation process, but ultimately contributing more material to the growing satellite. As the moon accumulated mass and its gravitational field strengthened, it began to clear its orbital path more efficiently. The process became self reinforcing. As the moon grew larger, its gravity could capture debris from farther away, which made it grow even faster. Within a few hundred years, the moon had swept up most of the material in the debris disk, leaving behind only scattered small fragments that would continue to rain down on both Earth and the moon for millions of years to come. The moon that emerged from this violent birth was very different from the world we see today. It was much closer to Earth, perhaps only 15,000 to 20,000 kilometers away, compared to the 384,400 kilometers that separate us today. At this distance, the moon would have appeared enormous in Earth's sky, subtending an angle of perhaps 20 degrees, about 40 times larger than the moon we know. This proximity had profound consequences for both worlds. The gravitational forces between Earth and the moon at this distance were tremendous, creating tidal effects that dwarf anything we experience today. If our current highest tides raise sea levels by a few meters, the tides created by the newly formed moon would have been hundreds of meters high. Of course, at this time, there were no oceans, just the molten surface of Earth, rising and falling like a slow planetary heartbeat under the moon's gravitational pull. The early moon itself was probably completely molten, its surface a global ocean of liquid rock heated by the constant bombardment during its formation. This molten state may have persisted for tens of thousands of years, as the moon slowly radiated away the enormous amount of thermal energy it had gained during its rapid accretion. Both Earth and the moon were tidally locked to each other during this early period, meaning they always showed the same faces to one another, just as the moon shows us the same face today. But because the entire Earth Moon system was spinning much faster than it does now, a day on Earth lasted only about 5 hours. Imagine experiencing nearly five sunrises and sunsets in what we now consider a single day. The rapid rotation and close proximity of the two bodies created a unique dynamic system unlike anything else in the solar system. The enormous tidal forces caused both worlds to bulge significantly in their mutual direction, creating a dumbbell like shape for the Earth Moon system as a whole. These tidal bulges would have been clearly visible from space had there been anyone to observe them. The heat generated by these extreme tidal forces helped keep both worlds molten much longer than they would have been otherwise. On Earth, the constant flexing of the planet's interior helped mix the molten material, ensuring that the differentiation process, the separation of heavy elements like iron into the core and lighter elements into the mantle, proceeded efficiently. The moon's close proximity also had important effects on Earth's early atmosphere. The powerful tidal forces in the atmosphere itself created massive atmospheric tides, regular expansions, and contractions of the entire atmospheric envelope that would have generated tremendous winds and weather patterns. These atmospheric dynamics may have played a role in stripping away Earth's early atmosphere and replacing it with gases released from the planet's interior through volcanic activity. As hundreds of thousands of years passed after the moon's formation, several important processes began to reshape both worlds. The most significant was the gradual recession of the moon from Earth due to tidal friction. This process, which continues today, though much more slowly, is caused by the transfer of rotational energy from Earth to the moon through gravitational interactions. Here's how it works. Earth's rotation creates tidal bulges in both the solid planet and its oceans. Because Earth rotates faster than the moon orbits, these bulges are slightly ahead of the moon in its orbit. The gravitational pull of these bulges acts like a weak brake on Earth's rotation while simultaneously pulling the moon forward in its orbit. This causes Earth's rotation to slow down gradually while the moon spirals outward to a higher, slower orbit. In the early days after the moon's formation, when the satellite was much closer and Earth was rotating much faster, this tidal recession would have proceeded much more rapidly than it does today. The moon might have moved outward by hundreds of kilometers per year compared to the 3.8 centimeters per year we observe today. As the moon receded from Earth, several dramatic changes occurred. The apparent size of the moon in Earth's sky gradually decreased from the enormous disk that dominated the early sky to something closer to what we see today. The tidal forces between the two worlds became less extreme, allowing both bodies to assume more spherical shapes, and Earth's days gradually grew longer as the planet's rotation continued to slow. The gradual cooling of both worlds also began to produce significant changes. The moon, being much smaller than Earth and having no atmosphere to trap heat, cooled more quickly. Within perhaps a million years of its formation, the moon had developed a solid crust, though its interior remained molten for much longer. This early lunar crust was probably much thicker than what we see today. The moon was still very hot from its formation, and volcanic activity was intense. Vast lava flows probably covered much of the lunar surface during this period, creating smooth plains that would later be disrupted by the continuing bombardment of asteroids and comets. Earth's cooling process was more complex and took much longer. The planet was larger and retained heat more effectively, but it was also still experiencing significant bombardment from leftover debris in the solar system. Large impacts would repeatedly disrupt the formation of a stable crust, remelting vast areas of the surface and preventing the establishment of permanent geological features. The formation of Earth's first stable crust was a gradual process that probably took tens of millions of years. As the rate of major impacts gradually decreased, small patches of solid rock began to form on the surface, only to be melted again by subsequent impacts. Eventually, these patches began to persist long enough to grow larger and merge with each other, creating the first continental masses. During this period, both worlds were still being heavily bombarded by asteroids, comets, and other debris left over from the solar system's formation. This bombardment peaked during what astronomers call the Late Heavy Bombardment, which occurred roughly 4.1 to 3.8 billion years ago. This period was responsible for creating most of the large craters we see on the moon today. The moon's surface preserves a nearly perfect record of this bombardment because it has no atmosphere or active geology to erase the scars of ancient impacts. Every crater tells a story of a cosmic collision that occurred billions of years ago. The largest of these impacts created the dark areas we call Maria, or seas, though they contain no water. These Maria are actually vast plains of hardened lava that flowed across the moon's surface after the largest impacts, filling in some of the deepest craters. Earth, meanwhile, was experiencing its own bombardment, but the evidence has been largely erased by billions of years of geological activity. Plate tectonics, erosion, and volcanic activity have recycled Earth's surface many times over, destroying most of the craters that would have formed during the late heavy bombardment. Only a few very large, very recent craters remain visible on Earth's surface today. But this bombardment had profound consequences for Earth's evolution. Many of the impacting objects were comets and asteroids that contained significant amounts of water, ice, and organic compounds. When these objects struck Earth, they delivered water that would eventually form our oceans and organic materials that might have served as the raw ingredients for life. The formation of Earth's oceans was a gradual process that probably began as soon as the planet's surface cooled enough for liquid water to exist. Water vapor released from Earth's interior through volcanic activity condensed in the atmosphere and fell as rain, while water from comets and asteroids added to the growing ocean basins. These early oceans were very different from the familiar blue seas of today. They were probably much smaller and shallower, and they may have been quite hot, perhaps approaching the boiling point in some regions. The water was also chemically different, containing high concentrations of dissolved minerals and gases from the planet's interior. But the moon's influence on these early oceans was immediate and profound. Even though the moon was farther from Earth than during its formation, it was still much closer than today, perhaps 200,000 kilometers away compared to today's 384,400 kilometers. The tidal forces created by the moon at this distance would have generated enormous tides, with water levels rising and falling by tens or even hundreds of meters twice each day. These massive tides had several important effects on early Earth. They mixed the oceans thoroughly, preventing them from becoming stagnant and ensuring that dissolved nutrients and gases were distributed throughout the water column. They also created vast tidal zones, areas that were alternately covered by water and exposed to airs that may have provided ideal conditions for the chemical reactions that led to the origin of life. Some scientists believe that these tidal pools created by the moon's influence were crucial laboratories for early biochemistry. The regular cycle of wetting and drying would have concentrated organic molecules, bringing them into close contact and facilitating the formation of more complex compounds. The energy from the moon's tides may have helped drive the chemical reactions that eventually led to the first self-replicating molecules. The moon's gravitational influence also began to affect Earth's rotation in ways that would have long-term consequences for our planet's climate and habitability. As tidal friction continued to slow Earth's rotation and push the moon farther away, our planet's days grew steadily longer and its axial tilt became more stable. The stabilization of Earth's rotational axis was crucial for the development of stable climate patterns. Without the moon's gravitational influence, Earth's axis would wobble chaotically over time, causing dramatic changes in the distribution of solar energy and making it difficult for complex ecosystems to develop and persist. Mars provides an example of what can happen to a planet without a large moon to stabilize its rotation. Mars has two small moons, but they're too tiny to provide significant rotational stability. As a result, Mars's axial tilt varies between about 15 and 35 degrees over cycles lasting hundreds of thousands of years. These variations cause extreme climate changes that make Earth's ice ages seem mild by comparison. The gradual lengthening of Earth's days also had important consequences for the planet's atmospheric and oceanic circulation patterns. When Earth was rotating every 5 hours, the atmospheric dynamics would have been dominated by the rapid rotation, creating circulation patterns very different from what we see today. As the days grew longer, more complex atmospheric systems could develop, eventually leading to the sophisticated weather patterns we observe today. The moon's influence on Earth's magnetic field, while indirect, was also crucial for our planet's long term habitability. The collision that created the moon also merged Thea's iron core with Earth's core, adding significant mass and helping to establish the powerful magnetic field that protects our planet from harmful cosmic radiation and solar wind. Without this magnetic shield, Earth's atmosphere might have been gradually stripped away by the solar wind, as appears to have happened to Mars. The moon's formation may thus have been indirectly responsible for preserving Earth's atmosphere and maintaining the stable conditions necessary for life to evolve and thrive. As millions of years passed, both Earth and Moon continued to evolve, but their evolutionary paths began to diverge significantly. Earth, being large enough to retain a substantial atmosphere and maintain geological activity, became increasingly complex. Plate tectonics began to reshape the planet's surface, creating the first mountain ranges and ocean basins. The atmosphere gradually changed composition as volcanic outgassing added new gases and chemical reactions in the oceans removed others. The moon, meanwhile, was settling into a more quiet phase of its existence. Its smaller size meant that it cooled more quickly than Earth, and by about 3 billion years ago, most of its internal heat had been radiated away. Volcanic activity gradually ceased, leaving the moon geologically dead, but preserving a nearly perfect record of its early history. The surfaces of both worlds during this period would have looked alien compared to what we see today. Earth had continents, but they were probably small and barren, with no life to green the landscape. The atmosphere might have been orange or red due to high concentrations of methane and other organic compounds. The oceans were smaller and may have been different colors due to dissolved minerals and primitive organisms. The moon's surface was darker than it is today, covered with the fresh basaltic lava flows that had filled the largest impact basins. The lack of weathering meant that these lava flows retained their dark color, creating the pattern of light and dark areas that we still see on the moon today, though much more subdued due to billions of years of micrometeorite bombardment. It was during this period, roughly 3.8 to 3.5 billion years ago, that life first appeared on Earth. The exact mechanisms of this emergence remain one of science's greatest mysteries, but the moon may have played a crucial role. The tidal mixing of the early oceans, the creation of tidal pools where organic molecules could concentrate, and the stabilization of Earth's climate may all have been necessary conditions for life to take hold. The earliest life forms were microscopic organisms that lived in the oceans and derived their energy from chemical reactions rather than sunlight. These primitive cells were remarkably hardy, able to survive in conditions that would be lethal to most modern organisms. They lived in a world with no oxygen in the atmosphere, intense UV radiation from the sun, since there was no ozone layer to block it, and frequent impacts from asteroids and comets. But these early organisms were also remarkably innovative. Within a few 100 million years of life's first appearance, some organisms had evolved the ability to harness sunlight through photosynthesis, a process that would fundamentally change Earth's atmosphere and climate. The oxygen produced by photosynthetic organisms gradually accumulated in the atmosphere, creating the oxygen rich environment that complex life requires. This oxygenation of Earth's atmosphere, known as the Great Oxidation Event, occurred roughly 2.4 billion years ago. It was actually a catastrophic event for many of the early life forms, since oxygen was toxic to the anaerobic organisms that had dominated Earth's early biosphere. But it also set the stage for the evolution of more complex, oxygen breathing organisms that would eventually lead to all the familiar forms of life we see today. Throughout this entire evolutionary history, the moon continued its gradual recession from Earth. By the time complex life began to evolve, roughly a billion years ago, the moon was already quite far from Earth, perhaps 300,000 kilometers away, compared to its current distance of 384,400 kilometers. The tidal forces were much weaker than during Earth's early history, but they were still strong enough to significantly influence the planet's rotation and climate. The moon's continued presence helped maintain Earth's rotational stability throughout the dramatic changes that occurred as life evolved from simple cells to complex multicellular organisms. This stability was crucial during several mass extinction events that punctuated Earth's history, allowing life to recover and diversify after each catastrophe. The most recent chapters of the moon's story have been marked by humanity's growing understanding of its nature and origin. For most of human history, the moon was a mysterious object in the sky, inspiring myths and legends, but remaining fundamentally unknowable. Ancient cultures around the world developed elaborate explanations for the moon's phases and movements, often incorporating it into their religious and mythological systems. The scientific revolution of the 16th and 17th centuries began to reveal the moon's true nature as a world in its own right. Galileo's telescopic observations showed that the moon's surface was not a perfect, smooth sphere, as ancient philosophers had believed, but a rugged landscape of mountains, valleys, and craters. This was humanity's first glimpse of another world, and it fundamentally changed our understanding of our place in the cosmos. Over the following centuries, astronomers used increasingly powerful telescopes to map the moon's surface in ever greater detail. They gave names to the moon's major features, often drawing on Latin terms that reflected their initial misunderstanding of what they were seeing. The dark areas were called Maria, or seas, because early observers thought they might actually contain water. The bright, heavily cratered regions were called terrae, or lands, distinguishing them from the supposed seas. By the 20th century, scientists had developed sophisticated theories about the moon's origin. Some proposed that the moon had formed alongside Earth as a double planet system. Others suggested that the moon was a wandering asteroid that had been captured by Earth's gravity. Still others believed that the moon had actually split off from Earth due to rapid rotation early in our planet's history, leaving behind the Pacific Ocean basin. Each of these theories had some supporting evidence, but each also had significant problems. The capture theory couldn't explain why the moon's orbit was nearly circular and lay close to Earth's equatorial plane. The fission theory couldn't account for the enormous amount of energy that would be required to spin off such a large piece of Earth. The double planet theory couldn't explain why the moon's composition was so similar to Earth's mantle, but so different from Earth as a whole. It wasn't until the Apollo missions of the 1960s and 1970s that scientists finally had the data they needed to solve the puzzle of the moon's origin. When astronauts brought lunar rocks back to Earth, laboratory analysis revealed crucial clues about the moon's formation that no Earth based observations could have provided. The Apollo samples showed that the moon's rocks had been formed at extremely high temperatures, much higher than would be expected from normal planetary accretion. They also showed that the moon was severely depleted in volatile elements, materials that would have been vaporized and lost during a high energy formation event. Most importantly, the isotopic composition of lunar rocks was nearly identical to that of Earth's mantle, suggesting that both had formed from the same material. These clues, combined with computer simulations of planetary collisions, led to the development of the giant impact theory in the 1970s and 1980s. This theory, which we've been exploring tonight, finally provided a coherent explanation for all of the moon's unusual characteristics and marked a revolution in our understanding of planetary formation. The giant impact theory also revealed something profound about the nature of planetary systems. The formation of the moon wasn't just an isolated event in Earth's history, it was part of a broader pattern of violent collisions that shaped all the terrestrial planets during the solar system's youth. Similar collisions probably occurred throughout the inner solar system, explaining many of the unusual characteristics of other planets as well. Mercury's unusually large iron core, for example, might be the result of a giant impact that stripped away much of the planet's rocky mantle. Venus's slow retrograde rotation might have been caused by a collision that knocked the planet spinning in the opposite direction. Mars's extreme topography, with massive volcanoes in one hemisphere and impact basins in the other, might reflect the aftermath of a collision that was less catastrophic than Earth's, but still dramatically reshaped the planet. Understanding the moon's violent origin has also changed how we think about the formation of planetary systems around other stars. The thousands of exoplanets discovered in recent decades show that our solar system is just one example of the many ways that planetary systems can form and evolve, but they also show that the relatively stable, well ordered arrangement of our solar system may be quite rare. Most of the exoplanetary systems we've discovered are very different from ours. Hubris many have giant planets orbiting close to their stars, or multiple large planets in complex overlapping orbits that would be unstable over long periods. The calm, predictable solar system we inhabit today is the end result of billions of years of violent evolution, with the moon's formation representing perhaps the most dramatic event in that long history. The moon's story also has important implications for astrobiology, the search for life elsewhere in the universe. If the moon has indeed played a crucial role in making Earth habitable by stabilizing our planet's rotation, moderating our climate, and creating tidal environments where life could evolve, then the presence of large moons around exoplanets might be a key factor in determining their habitability. Unfortunately, detecting moons around exoplanets is extremely difficult with current technology. The planets themselves are barely detectable as tiny dips in their host star's brightness, and their moons would create even tinier signals. But as our observational capabilities improve, we may eventually be able to identify exomoons and study their potential effects on planetary habitability. The moon continues to be an active subject of scientific research, with new discoveries regularly revising our understanding of its history and composition. Recent missions have revealed that the moon is not the dry, dead world we once thought it was. There's water ice in the permanently shadowed craters at the moon's poles, and there may be as much as 1 billion tons of water hidden beneath the lunar surface. This water is itself a relic of the early solar system, delivered to the moon by the same comets and asteroids that brought water to Earth. Some of it may date back to the moon's formation, trapped in the lunar interior, and gradually released over billions of years. In a sense, the moon has been patiently preserving some of our solar system's most precious resources, waiting for us to develop the technology to discover and perhaps one day use them. The discovery of lunar water has transformed our plans for future space exploration. Water can be split into hydrogen and oxygen, rocket fuel, and breathing gas, making the moon a potential stepping stone for missions to Mars and the outer solar system. NASA's Artemis program, which aims to establish a permanent human presence on the moon, is specifically focused on the water rich polar regions where future lunar bases might be able to operate sustainably. But beyond its practical value for space exploration, the moon continues to serve a deeper purpose as a source of wonder and inspiration. Every clear night, millions of people around the world look up at the moon and feel a sense of connection to something larger than themselves. The moon has inspired countless works of art, literature, and music throughout human history, and it continues to capture the imagination of each new generation. There's something profoundly moving about the realization that this beautiful, peaceful presence in our night sky was born from one of the most violent events imaginable. The moon represents the ultimate transformation of destruction into creation, chaos into order, violence into beauty. Its very existence is a testament to the creative power of the universe and the remarkable processes that can emerge from apparent disaster. The moon's phases, which have marked the passage of time for human civilizations throughout history, are themselves a consequence of the cosmic collision that created it. As the moon orbits Earth, we see different portions of its sunlit surface, creating the familiar cycle of new moon, crescent, quarter, gibbous, and full moon that has served as a calendar for cultures around the world. This lunar calendar is more than just a convenient way to mark time. It's a direct connection to the cosmic forces that shaped our world. Every time we observe the moon's changing phases, we're witnessing the continuation of the gravitational dance that began 4.5 billion years ago when two worlds collided and created the Earth Moon system we know today. The moon's gravitational influence continues to affect Earth in ways both obvious and subtle. The most visible effect is the twice daily rhythm of the tides, which rise and fall in response to the moon's position in the sky. These tides are much weaker than those that existed when the moon was young, but they still play important roles in Earth's climate and ecology. Coastal ecosystems around the world are synchronized to the lunar cycle, with countless species timing their reproduction, feeding, and migration to coincide with specific phases of the moon. Many marine organisms release their eggs and sperm during particular lunar phases, taking advantage of the highest tides to disperse their offspring. Some birds and other animals use the moon's light for navigation during long migrations. Even human biology may retain some connection to lunar cycles. The human menstrual cycle averages about 29.5 days, remarkably close to the moon's 29.5-day phase cycle. While this similarity might be coincidental, some researchers have suggested that our ancestors' reproductive cycles may have been synchronized to the moon, just as many other animals' cycles are today. The moon also continues to influence Earth's rotation, though the effects are now much more subtle than they were in the early solar system. The moon is still gradually receding from Earth at about 3.8 centimeters per year, and Earth's rotation is still slowly decreasing as a result. Our days are getting longer at a rate of about 2.3 milliseconds per century, not much by human standards, but significant over geological time. This gradual slowing of Earth's rotation has been going on for billions of years, and it will continue far into the future. Eventually, perhaps 50 billion years from now, Earth and Moon will become tidally locked to each other, just as they were shortly after the Moon's formation. At that point, both worlds will always show the same face to each other, and a day on Earth will equal a month lasting about 47 of our current days. Of course, long before that happens, our sun will have evolved into a red giant star, probably making Earth uninhabitable. But the fact that we can predict the Earth Moon system's evolution so far into the future demonstrates how well we understand the gravitational forces that have been shaping our world since its violent birth. The moon's story is ultimately a story about time and change on cosmic scales. When we look at the moon tonight, we're seeing the end result of processes that began before life existed on Earth and that will continue long after our species has vanished. The moon connects us to the deep history of our solar system and reminds us of our place in the vast sweep of cosmic evolution. But the moon's story is also deeply personal and human. Every person who has ever lived has shared the same view of the moon that you see tonight. Ancient astronomers in Babylon and Egypt studied the same lunar surface that Galileo observed through his telescope and that Neil Armstrong walked upon. The moon has been humanity's constant companion throughout our entire evolutionary history, influencing our biology, inspiring our cultures, and guiding our first tentative steps into space. The moon represents both continuity and change continuity in that it has remained essentially unchanged throughout human history, and change in that our understanding of its nature and origin has evolved dramatically. Our ancestors saw the moon as a goddess or a celestial chariot, while we understand it as a world born from cosmic collision. Yet the sense of wonder and mystery it inspires remains the same. As our species prepares to return to the moon and establish a permanent presence there, we're entering a new chapter in the long relationship between Earth and its satellite. For the first time in the moon's 4.5 billion year history, one of Earth's species has developed the capability to travel to the moon and potentially alter its pristine surface. This capability brings both exciting opportunities and profound responsibilities. The moon may hold resources that could support human expansion into the solar system, and it certainly holds scientific treasures that could revolutionize our understanding of planetary formation and early solar system history. But the moon is also a unique and irreplaceable natural laboratory, preserving a record of cosmic processes that has been erased from Earth by billions of years of geological activity. As we plan for humanity's return to the moon, we must balance our desire for exploration and resource utilization with our responsibility to preserve the moon's scientific and cultural value for future generations. The moon belongs not just to us, but to all the generations of humans who will come after us, and to the countless other species on Earth whose lives are influenced by the moon's gravitational pull. The moon's formation story, also offers important lessons about resilience and transformation. The collision that created the moon was undoubtedly one of the most destructive events in Earth's history, melting the entire planet and nearly destroying both worlds involved. Yet from this destruction came something beautiful and beneficial as a satellite that has helped make Earth habitable for billions of years. This pattern of creative destruction appears throughout the universe. Stars are born from the collapse of gas clouds, but they also die in spectacular explosions that seed space with the heavy elements necessary for planet formation. Galaxies grow through violent collisions that trigger massive bursts of star formation. Even life on Earth has been shaped by catastrophic events, mass extinctions that clear evolutionary niches for new forms of life to emerge. The moon's story reminds us that even the most catastrophic events can lead to positive outcomes that we couldn't have imagined beforehand. The collision that created the moon nearly destroyed both worlds, but it ultimately created the conditions that allowed our planet to support the incredible diversity of life we see today. As you prepare for sleep tonight, perhaps you'll find comfort in this cosmic perspective. The challenges and difficulties we face in our daily lives, while real and important to us, are part of the same ongoing process of change and adaptation that has shaped the universe since its beginning. Like the moon that was born from cosmic catastrophe, we too have the capacity to transform challenges into opportunities and to create something beautiful from apparent disaster. The moon that shines down on you tonight has witnessed the entire history of life on Earth. It has watched as the first primitive cells learned to harness sunlight, as complex multicellular organisms filled the oceans, as life colonized the land, as consciousness emerged, and as our species developed the capacity to understand our own cosmic origins. It has been a silent guardian throughout this entire remarkable journey, helping to maintain the stable conditions that made it all possible. In its ancient light, we can find both humility and inspiration. Humility at the vast scales of time and space that dwarf our individual lives, and inspiration at the remarkable processes that brought us into being. We are, quite literally, children of the cosmos, shaped by stellar explosions, planetary collisions, and billions of years of evolution. The moon above us is both a companion in this cosmic journey and a reminder of the creative power that operates throughout the universe. The story of the moon's formation is also a story about the power of scientific inquiry to reveal truth. For thousands of years, humans looked at the moon and wondered about its origin, creating myths and legends to explain its presence. But through careful observation, experimentation, and theoretical work, we finally uncovered the moon's true story, a story far more remarkable than any myth our ancestors could have imagined. This achievement represents one of humanity's greatest intellectual accomplishments. We've learned to read the signatures of ancient events preserved in rocks and to use the laws of physics to reconstruct events that occurred billions of years before our species existed. We've built machines capable of traveling to other worlds and bringing pieces of them back for study. We've developed mathematical models that can simulate the collision of planets with remarkable accuracy. In the process, we've discovered that we live in a universe far more dynamic and interconnected than our ancestors ever suspected. The moon is not just a beautiful object in our night sky, it's a key player in the complex system of gravitational interactions that keeps our planet habitable. Its formation was not an isolated event, but part of a broader pattern of violent collisions that shaped all the terrestrial planets. Understanding the moon's origin has also given us a new appreciation for the rarity and preciousness of our world. The collision that created the moon had to occur at just the right angle, speed, and time to produce the stable Earth Moon system we see today. A slightly different collision might have destroyed both worlds entirely or created a system that couldn't support life. The moon's presence has been crucial for maintaining Earth's habitability over billions of years, helping to stabilize our planet's rotation and create the tidal forces that may have been essential for life's evolution. Without the moon, Earth might have remained a lifeless world, beautiful perhaps, but empty of the incredible diversity of organisms that we see today. This realization should fill us with both wonder and responsibility. We are incredibly fortunate to live on a planet with conditions so perfectly suited for life, and much of that good fortune stems from a cosmic collision that occurred before our solar system had even finished forming. The moon above us is not just a companion world, it's one of the key reasons why we exist at all. As you settle into sleep tonight, let your mind wander across the vast expanses of time we've explored together. Picture the young Earth glowing like a small star in the aftermath of the moon forming collision. Imagine the debris disk slowly coalescing into our familiar satellite. Think about the billions of years of patient recession as the moon gradually moved to its current orbit, helping to create the stable conditions that allowed life to evolve and flourish. Consider the remarkable chain of events that led from that ancient collision to this moment. As you listen to these words under the moon's gentle light, the collision merged the cores of two worlds, creating Earth's magnetic field. The moon's tides mixed the early oceans and may have helped life make the transition from sea to land. The moon's gravitational influence stabilized Earth's rotation and created the predictable climate patterns that complex ecosystems require. Every aspect of our existence is connected to that ancient cosmic catastrophe. The iron in our blood came from the merged cores of Earth and Theia. The water in our bodies may have been delivered by the same comets that continued to bombard both worlds for hundreds of millions of years after the collision. The oxygen we breathe was created by organisms that evolved in tidal pools shaped by the moon's gravitational pull. We are not just observers of the cosmic story, we are active participants in it. Our species has developed the unique capability to understand our own origins and to contemplate our place in the universe. We can look at the moon and see not just a beautiful celestial object, but evidence of the violent creativity that characterizes cosmic evolution. This perspective can be both overwhelming and comforting. Overwhelming because it reveals the vast scales of time and space within which our lives unfold. Comforting because it shows us that we are part of something much larger than ourselves, participants in a cosmic story that began with the Big Bang and continues to unfold around us every day. The moon that watches over your sleep tonight is the same moon that has inspired countless generations of humans to wonder about their place in the cosmos. Ancient peoples used its phases to mark the passage of time and its position to navigate across trackless oceans. Poets have written about its beauty, lovers have made promises under its light, and children have wished upon it throughout human history. Now we know that the moon is even more remarkable than our ancestors imagined. It's not just a beautiful ornament in the night sky. It's a world born from cosmic fire, a guardian that has helped protect and nurture life on Earth for billions of years, and a constant reminder of the dynamic creative forces that operate throughout the universe. As you drift towards sleep, perhaps you'll dream of that ancient collision of two worlds becoming one planet and one moon, of the slow dance of gravity that has been ongoing for 4.5 billion years. Dream of the moon as a young world, glowing with the heat of formation, gradually cooling and moving away from Earth as both worlds settled into their cosmic partnership. Dream of the first life forms that emerged in tidal pools shaped by the moon's gravitational pull, and of the long evolutionary journey that led from those primitive cells to the incredible diversity of life we see today. Dream of the moon as humanity's first destination beyond Earth, and of the future generations who will walk on its surface and perhaps make it their home. The moon's story is our story, because we are all children of the same cosmic processes that shaped our solar system. In the moon's ancient light, we find both our origins and our destiny, that the creatures of stardust and collision, shaped by forces vast and beautiful, capable of understanding our own place in the grand cosmic story that continues to unfold around us. Rest well tonight, under the moon's protective gaze, knowing that you are part of an ancient partnership between worlds, a relationship forged in cosmic fire and tempered by billions of years of patient evolution. The moon above you carries the memory of our planet's most violent transformation and stands as eternal proof that even from the greatest destruction, the most beautiful and beneficial outcomes can emerge. Sweet dreams, fellow travelers in this cosmic journey. May your sleep be filled with visions of worlds in formation, of cosmic creativity, and the profound forces that brought us all into being. And may you wake tomorrow with a renewed sense of wonder at the remarkable universe we inhabit and the incredible story of which we are all part. Thank you for joining me on this epic journey through deep time to witness the birth of our moon. If you've enjoyed this exploration into the cosmic events that shaped our world, please consider subscribing to Sleep About Science for more gentle adventures into the wonders of our universe. Leave a comment and let me know where you're listening from tonight. I love knowing that people all around our moon-blessed planet are sharing in these moments of cosmic wonder. And if you found this journey meaningful, a gentle like helps other seekers of sleepy science discover these explorations. Wherever you are in the world, whatever time it is where you're listening, may your dreams be filled with the beauty of celestial creation and the profound realization that we are all stardust, shaped by cosmic forces into conscious beings capable of contemplating our own magnificent origins. Sleep well under the light of our ancient companion, and good night.